you for having me, and it's always a pleasure to speak in front of enthusiastic students. And so I guess, as always, as I like to plug my 4950 class, and so I always lecture my 4950 class. I lectured them at the beginning of the year about what topics to give, and how to choose a good topic. And so I tried to think of, and so in this talk, I guess my main goal will be to try and convince you that this idea, so there's always this question of whether we create mathematics or whether it exists naturally. And so I'll try and convince you that this idea exists naturally. It's organic, and so it's very beautiful, I guess we want to say. And so, okay, with that, so with that, I'll get started, I guess. So exactly, so one of the toughest concepts I had as an undergrad was this idea of dimension. Right, all my professors would draw a ball, and then they would say, well, the inside of the ball is three-dimensional, and the boundary of the ball is two-dimensional. And I never quite understood that, and so hopefully, I wanted to make this title a little bit as unscary as possible. And so we know length, area, volume, and hopefully dimension. So obviously we have to start somewhere. So suppose we have we have an interval AB subset of R1, right? So suppose we just have the real line. So we always have to start somewhere. So assume we all know what the real line is. Here's A, and here's B. And so then we want to ask the length. So the length of this set of this interval AB. I guess this is where we'll start out at. So what do we think? What do we always say that this length of this interval is? Absolute value. Okay, very good. Absolute value of b minus a, right? So I've kind of tried to draw b minus and b bigger than a here. So so you all are thinking better than me already. And so again, exactly in R2, we have A, B, C, D. So we have this rectangle. And so the area, so we have this idea of area, right? So this area of AB cross CD is equal to exactly just the multiplication of the lengths of these sides, B minus A times C minus D, or D minus C. Very good. So we have to start out somewhere. So this is what we're going to assume we already know. And so, but you can even, if I wanted to make this talk even longer, you could ask yourself, why should this even be true, right? Why should I start out and say, why should this length of this line be AB, and why should the area of this square be this? Why do we have that? I mean, it's not obvious, right? It's just what we're always told. If at the very end of the talk, if I have some more time, we'll actually come back to that question, how we might come back to that. So I promised you all some, I always like to point out in my students' lectures where they give very good references to past classes they've had. So where have we seen area before?
Are we plugging geometry or like calculus here?
Anything, Eddie. You can say anything. Where have we seen area? Where's maybe the first place you've seen area? I guess so. I guess in maybe after geometry, right? So geometry, you're after geometry. I mean, geometry is basically based on this idea that the rectangle has this area, right? So we get areas of triangles and such. So I'll give you a hint, maybe calculus. Where we said
integrals.
Integrals, right? Exactly. So the area, we've seen the area underneath the curve, right? So
I was gonna say, I remember it more first from grid paper.
Grid paper.
To shade the squares.
Exactly. So this, I mean, that goes back to this, right? Exactly. So, very good. Yeah.
Determinants too.
Yes. Yes, exactly. So there's lots of places. I gotta be careful when I solicit information because if I get the wrong answer, then I have to take what I get, right? And so here's my y equals f of x. And so exactly we found the area. We supposedly, I told you what the area was. We found the area underneath this curve, right? And so how did we find this area?
Use subrectangles.
Do what?
A Riemann sum.
Yes, exactly, a Riemann sum, exactly, very good. So right, you broke this interval up into subintervals, I always told my class, and then we estimated the area on each subinterval by a rectangle, right? And so I'll draw these, draw my rectangles that I'm going to approximate my area by. So we approximated. So again, there you probably didn't even think about it, but you were assuming that the area of these rectangles was exactly what you've always been told, and we approximated the area by rectangles. And made them very small. Small to better approximate. Right? And that's exactly what we did. So we just shrank. All we had to do, so this is a very special region, right? Because it's the area underneath the graph, and so the bottom's all flat and the sides are all flat. So all we had to do is we just had to shrink these rectangles up, and so they would better approximate them just really, really skinny, right? And so the function wasn't changing so much, or function was always assumed to be continuous in order to do these special types of areas. And so in the exact same thing with volume under the graph. Z equals f of x, y, right? Exactly. So, you know, you had a graph of a function in 3 dimensions that sat over a domain in our x, y, z plane. Sat over a domain in the x, y plane in space, and then you did the exact same thing again. You broke up your domain into small little grids, into small little rectangles, and then over the rectangle you approximated the volume above this rectangle by a cube, right? By a higher dimensional cube, one higher dimensional cube, and then you sent these guys getting smaller and smaller, right? And you did this throughout. Right? So find the volume. Very good. And so now the question is suppose now I just have a general region or set in R2. Right? So here's my R2, and now I just have it's not a region underneath the curve. It's just a set, but it looks like you might be able to, you know, it has this, I draw it sort of nicely, and so it looks like it has an interior that we could try and figure out the area of. So what? So then we could ask. So here's my A. So what is the area of A? But we don't know. So yeah, and so I guess so you could figure out the A by doing. I guess you could think about the volume of the graph of the function of just 1 over this region, right? And figuring out that volume, but it would still have to involve you figuring out the area of here. But I guess the point is that this region is just we don't know. It's not described in a nice way, right?
So you're not intending top curve minus bottom curve.
Exactly. So I tried to draw it all squiggly, and so I guess we always take for granted the very nice objects we're given in calculus. But it still looks kind of nice. And so I'm just saying, if you had suppose this was your yard and you had a fence that outlined your yard like this, and you wanted to find how many square meters your yard was, what might you do?
I'll bring up the first thing I mentioned, grid paper.
Grid paper, exactly, right? Exactly, very good. Grid paper. So how does grid paper work? Well, I just start drawings. Rectangles.
Yellow tape lines every meter across or something.
Exactly. So you can draw grids inside of here. So draw little rectangles. So we know. So I guess the point is that we know the area of a rectangle, right? That's basically all we know. And so we're just going to draw as many rectangles in here as we can. Keep drawing rectangles, but then if I keep using this size of rectangles, I'll hit up to here, and so maybe I'll draw a little bit smaller rectangles. Right? And so maybe how should we define our area? So if we wanted to do this in a very mathematical way, we could say that the area of A is equal to, well, let's just take a bunch of rectangles. So I'll do it. We'll do the wrong way first, and then we'll do the right way. So the way I've drawn it here, and so you take all these rectangles that fit inside, right, and you add up their areas. So we take all the areas of rectangles. So Ri. We sum up all the area of Ri, such that Ri is a subset of A. And what else do we need? What else do we want to be true about these rectangles?
They're just drawing.
They're just joined. Very good. Very good. So Ri intersect Rj equals empty set if I is not equal to j. Right? Disjoint rectangles. So fill it up with disjoint rectangles. We take this. So we take a bunch of rectangles that sit inside of it. They're disjoint, and then we add up the areas of them. But they're not going to be exactly perfect, right? So because this curve is going to be covered it. So if we take any set of these Ri's that satisfy these properties, then what's the final thing we want to do with these numbers?
Soup.
Take the soup. Very good, very good. So I didn't know if there's going to be any freshmen or sophomores in this class. And so if you don't know the soup, then you just think of the maximum, right? So soup is equivalent to a maximum if you haven't taken analysis yet. So this is one way to do it. But then an even easier way. So the easy way. So I tried. So hopefully I tried to maybe give a hint in this picture. So in maybe if you take an advanced calculus, you did an integral, and you did an upper sum and a lower sum, right? So the integral existed if the upper sum was equal to the lower sum, right? Very good. So this you can imagine as sort of the lower sum, right? So how would we take the upper sum?
So you want rectangles whose
intersection with A isn't empty?
Yeah. You wouldn't want to count those, but instead of taking a soup, what would you take? An inf, right? So that sort of cancels out that, right? So if you're taking an inf, then you wouldn't have to worry about rectangles not meeting your sets. But what do you want to be true? If I take a bunch of RIs and I want to take the inf of the sum of these areas, what has to be true about these rectangles in the area? What has to be true about them? So before, the rectangles had to be all contained inside of A. But how should A be?
Yeah, that's what I was saying. They have to have a non-empty intersection.
Well, I mean,
right?
so they don't necessarily.
It's not there.
Yeah, exactly. They don't necessarily. If I added in, so now here's my new picture.
It's more like A should be contained within the sum of the rectangles.
Very good, very good, Eddie. So very good. So before, the rectangles had to be contained inside of A, right? But if I want to take the infimum now, I want now I want the A to be contained inside. I want them to cover, right? So we're so used to using covers in math, hopefully. And so A.
You were looking for people to not say every single rectangle contains A.
Right.
Yeah.
Not every. Say that again.
You didn't want every single one of the RIs to contain A. You wanted their union to contain A.
Exactly, yeah. I want their union to contain A, exactly, yeah. And so hopefully you see from this that two things we don't need to be true now. So exactly, we don't need to worry about rectangles not being intersecting A. I can add in this, but then we're taking the inf, right? So we could take covers that don't include that, and that would take care of that. And also, we don't need to worry about them being disjoint, right? Because we can take any cover and make it disjoint, any countable cover and make it disjoint. So we don't even need to worry about that. So that looks pretty good. Very good. So the RI are rectangles, right? So RI.
Not to bust. Does something bad happen when we talk about uncountable covers?
Does something bad happen? In this case, so then the question is how do you sum up an uncountable?
Oh,
number
okay,
of
all right,
covers?
that's fair.
Which is possible, but that's an even that's another can of worms, right? So yeah, very good. So you can sum up an uncountable number of numbers, but that's you got to figure out a way to do it, and that's a little bit more complicated. So here exactly. So here we're taking the sum, and so we can even take countable covers, and the same thing here too. It could have been countable here. So so technically, so then. What's the next thing I want to say? So in the exact same thing, we can do, and for omega subset of R3, so here's my weird looking set in R3, we can do the exact same thing, with cubes. So the cubes, so we would take, so the volume of omega is equal to the infimum of the sum of the volume of CIs. I'll call them CIs. CIs such that omega is a subset of the union of CIs. Exact same definition, only now CIs are cubes. Except now the CIs are cubes instead of rectangles because we're in 3 dimensions now. And notice here we were in R3, and here we were in R2, and we can do the exact same thing for length in R1. So, and measure, so what we call these things, so this this area, let's call this guy, let's call this area star. These area and volume are called just for your note. Lebesgue 1 and Lebesgue 2 outer measure. So some people get kind of uptight about what you call a measure and what you call an outer measure. So you can guess why these are called outer measures, right? And so this is just in case you've ever heard of Lebesgue measure. This is exactly what Lebesgue measure is. We took so Lebesgue 2 measure is what we think about as area. And sorry. This is Lebesgue 2 and Lebesgue 3. Sorry. So Lebesgue 2 was area and Lebesgue 3 was volume. Lebesgue 3 was volume. Okay. And so Lebesgue 1 is length. So these seem, so hopefully this seems very intuitive to you. And so it just seems like a very natural way. Hopefully I convinced you that the outer measure just seems a little bit more easily defined and easily grappled with.
The outer measure is the one with the nth.
Yeah.
Yes, exactly,
Okay.
exactly. Outer measure is you're covering it with outer,
Yeah.
right? Outer, and so so yes, exactly. And then just like you had, and then if you're in a finite, I probably shouldn't say that, but and then analogous upper sums and lower sums and integrals, you have outer measures and inner measures or measures, which we don't even know what a measure is yet, so I shouldn't use that word. So notice we were only dealing with area in R2 and volume in R3, right? So area is like you think of the area of a two-dimensional thing we measured it in R2, and the volume of something existed in R3. But we have seen we have seen examples of measuring lower dimensional objects in higher dimensional space. Does anybody want to volunteer the answer that I'm looking for? I won't accept answers that I'm not looking for.
Arc length.
Arc length, very good, right? Exactly, arc length. So in calculus, in calculus 2, I guess, in calculus 2, we find the length of the curve. Let's call them. I'm not calling them curves. Gamma. Gamma defined by y equals f of x. So again, we have the exact same picture between A and B. So here's my A, and here's my B, and here's my y equals f of x. Maybe let's just cut it off at A and B. That's what my notes probably say. Cut it off at A and B, so we're not confusing anything. So here's a nice looking curve, and so we exactly said we calculated the length of this. So the length of gamma is equal to, so this is the integral from A to B, so just rewriting our f of x, rewriting our formula that we all memorized, but we don't remember where it came from. There's length of gamma, right? And so how did we get this? Well, we did it just by exact same thing, remember? So we just broke up our interval. So we broke up our interval into small sub-intervals, and then we drew lines. Drew lines between those points, and we thought, oh well, this line is probably about as long as the curve is on that interval, but then it gets even better as we shrink the intervals, right? And then shrink the intervals. So we estimated. So again, all we know are lengths of lines and areas of rectangles and volumes of cubes. That's all we've been using so far. And I think we always take it for granted when we do that in math. Nobody ever asked the question, why is the area of a rectangle this? We estimated the length of the curve. Length of gamma with the straight lines. And made sub-intervals. Smaller. But now here's where the problem comes in. So, and again, you can do the exact same thing. For a surface area of z equals f of xy in R3. Right? So if this function is differentiable in x and y, we estimated, remember you estimated the area, the volume underneath the surface by a parallelogram going in two different directions. I promised myself I wasn't going to draw on 3 dimensions, but here I am. So you took the value of the function at this point. You went a little bit in the x direction and measured the value in this at this point. So this is xy, f of xy, and then this is x plus delta x, y, f of x plus delta x, x plus delta x, comma y. And so, and then this is the other corresponding point, right? And so then you took these two vectors and you took the parallelogram that they span, which may or may not, it sits, above or below, or not neither, with relative to the surface, and then we shrank those down, right? And so again, we estimated surface area with parallelograms. Which you can get for free from the rectangles. So here's the problem. Here's the problem. Suppose we have something that looks like a curve in R2, but we don't know a parameterization for it. So the definition of a curve, I guess, to learn in differential geometry is something that you can map the line into the plane and the line into space, right? And so I might give you a subset. So I might give you a subset in R2, but I don't give you the parameterization, right? I might draw a line might draw a line on your paper, but you don't know what that line is defined by or where it came from. It looks like it's a nice clean line that should have a length to it. So what's the problem? So we have to think about how we would find the length of this line. How would we find the length of gamma? Right. I mean, this doesn't seem. This doesn't seem. So I guess when I was first thinking about this, talking to Mo yesterday, he reminded me. So if you want to do the secant example, it implies some sort of parameterization. You have some order. You have some sort of order on your curve.
Or are you given like an equation that the curve satisfies?
No, not even that. Not even that.
Do you at least know, like, if a point is on a curve or not? Like.
Yeah.
Okay.
So you're given a subset. You're given a subset. So you give me a point. I can tell you whether the point is in the set. But other than that, that's all I can tell you.
And it's a subset of R2.
It's a subset of R2, right? And it looks like this, though. It looks like this. So,
I mean, if it looks like this, you could like take string and glue it to the board and then.
very good.
Right.
Very good. Very good. Right? Exactly. Exactly. You would want to take string and glue it to the board. That's exactly what you would want to do. And then straighten it out, right? And then straighten it out. Exactly. And so maybe, I don't know. And so I mean, the best thing I can do to try and do that is maybe try and glue little straight lines to the curve, maybe, right? And so maybe if you just go along taking these little straight lines, that might. So just maybe trying to adapt our covering technique for that we had for Lebesgue measure, right? So we had something that was two-dimensional. In R2, we thought maybe we could cover it with rectangles. Here, maybe I'm trying to figure out, well, I have something that looks like it might be one-dimensional, and then why can't I cover it with lines, right? Why can't I cover it with straight lines? And it should be very intuitive that it would take me an uncountable number. Even if this was a nice clean curve, a nice smooth curve, it would take me an uncountable number of little straight lines. I mean, I might have a little straight line like that, but that only covers 2 points, right? So our covering technique doesn't work. And then yeah, exactly. And so you have this extra dimension where these lines can wiggle. So that's the problem. And so the tactic, right? So the secret or the trick. So here's my curve again. So before. So I guess the point is that when we try to find an area of a subset in R2, we took the rectangle and then we took the area of the rectangle, right? So now the goal is I'm going to cover. So it works just as good with rectangles, but I'm going to use balls. I'm going to cover my. I'm going to cover. I will cover. Covering just seems like an easy thing to do, right? It's easy to test whether something's a cover, right? It's a set theoretic condition. I will cover gamma by balls, right?
Disjoint or just?
Oh, we'll see. We'll see exactly.
We'll see.
Yeah, we'll see exactly. So again, what got rid of the condition with disjointness was that we required them to cover, right? And so it behooves you. We required it to cover, and then we took an infimum, so it behooved you to not have them overlap. And so it doesn't matter if they're exactly. So you can have them disjoint. You can have them overlap. by balls, and the length. If this curve is really nice and the ball is really small, and you situate the ball in an optimal point, so I mean I can put a ball on here that sits like that, but that doesn't do so well. I might as well sit it a little bit lower and cover more. And so, and the length, sometimes what I'm saying, I'm thinking it's not matching with the board. I will cover the balls, and the ball is really small. The length and gamma is, and right now we're assuming gamma is nice, is like almost like a one-dimensional thing. The length of gamma inside a ball is about what value? Exactly, about the diameter is about the diameter, right? And so again, we'll do the exact same thing, right? So let's do this, the length of gamma. We'll do the exact same thing. We'll sum it up. So we're going to sum up the diameters of BI. So such that gamma is contained in the union of BI. Right? And now what's the problem? So there's a little bit of a problem.
They overlap.
If they overlap, well, okay, so exactly, so the overlap, so we're eventually going to take what? Take the infimum, right? Okay, but there's still a little bit of a problem in that we want to keep track of how well these balls are approximating my curve, right? So if I had a really slowly dying spiral, right? That almost filled up a circle, I could cover it with a ball of a diameter that, right? But the length of the curve inside that ball is not about the diameter, but it seems like I'm cheating there, right? So just like we had when we found the areas of areas under curves in calculus, we had to force the rectangles to get really small, right? So here we'll have to do the exact same thing to approximate our curve, and we want to force these balls to get really small so that they keep track of the object we're looking at, right? And so let's keep track of that. So the diameter of my BI is less than or equal to less than some delta. And so I'm going to keep track of that with a little parameter right here, delta. And so my delta length of this guy is I take all the covers that have the diameters of their balls less than delta. I look at all those covers, I add up the length of their diameters, and then I take the infimum over those numbers, right? And then what do you think we should? What do we think we should let the final length be? What do you think we should let delta go to? 0. Very good, right? Exactly. Just like in calculus. So then to find the final length, take the limit as delta goes to 0 of L delta of gamma. Call this L of gamma. Right? And so then your first question should be was why does this exist? Right? So maybe I'll just tell you. So this exists because since we're taking the infimum over covers, requiring that their diameters are not that big, then the subset of covers is decreasing as you decrease delta. You're taking the infimum over all those, and so this parameter, this value L delta of gamma, is increasing as delta goes to 0. Yeah, Robert.
Question. You said you don't know like the points on this. So how do you know where to draw the balls at? Like, you know, you're gonna take a guess and you say like A is gonna be like the center. Like, I mean, so how do I know where to draw the ball at?
You don't know where to draw the ball, but since you're considering all covers, then it just works out, right?
No, I mean, like you said, like you didn't know anything about the line, so like
We know if an element's,
Yeah,
know
well-
if something is an element of a line.
Yeah.
Oh, okay. I thought
But
you
we
yeah,
don't
okay.
know parameters.
No, yeah.
Oh, okay.
I can tell you whether a point is in the set or not, right?
Oh.
So it'd be kind of like you asking your computer, is this point? Your computer can graph you a line, but if you don't know where it came from, then you can't ask your computer anything more, right? I mean, maybe the computer knows, but. So that's exactly, yeah. So you know what points are in this set, but the point is that you don't know the parameterization.
Okay.
Right? So you just kind of know what it looks like. And so I'm just drawing these really nice. We're gonna see bad examples here a little bit. So I don't want to. Yeah. So that's gonna be the fun part of play.
So does that curve spiral in, is it infinitely long, or did you?
It depends how fast it spirals, right? Depends how fast it spirals. So exactly. So okay. So maybe this exactly maybe you might answer your question here. And so this exists because L delta of gamma is increasing as delta goes to 0, right? So it's monotonic. It's monotonic as delta goes to 0. And so, but I mean, in particular, it can't be infinity. You can have a length of a line be infinity. So, very good.
So could it be defined by taking like a double inf, so to speak?
You have to be careful. It's almost an infinite a soup. I mean, because this number is getting bigger as delta is going to 0. Yeah. It's a very commonly used tool in analysis. So very good. So now we've done length. So now let's do a general. So now suppose I have a set but I have no idea what dimension it is. So maybe I'll keep this in R2. So I have this. Maybe I'll draw it like that. So you can't tell whether it's a curve. You can't tell whether it's a big plane. So maybe I should point out maybe before I get to this. Maybe let's do a couple more examples. So we can repeat this procedure. For curves in R3. Right, so if I have R3 here, and I have a curve, the only difference is now I cover it with a ball, and a three-dimensional ball. All right. I cover it with three-dimensional balls because I'm in R3. I can cover it with three-dimensional balls, but it'd still be the diameter, and the length of the line would still about approximately be diameter of gamma intersect BI is still approximately the diameter of BI, right? But then I can also do the exact same analogous thing for a surface in R3. So suppose I had really nice looking surface in R3 that's exactly like a curve in R2, right? So this is surface subset of R3, right? So again, you can think about covering it with three-dimensional balls. And if you position, but then the area of S intersect the BI is going to be approximately what?
Those circles, right?
Yeah, exactly, right? So you'll get little tiny circles in here, right? Exactly, two-dimensional circle. Very good. So then this is about, so we'll have to divide. So we'll have to take the diameter of these BIs. So we'll see why I insist on using diameter. So we said diameters to begin with, but so we'll find the radius just by taking diameter and dividing by 2. You'll find out why I insist on taking this, and then multiply by pi. That's the area of a circle, right? Somebody told me that one time. So, but that doesn't matter too much. We don't care about that too much. And we'll see why. Okay. So, so very good. So now back to this question. Very good. So now we've seen we can do the exact same thing for curves in R3 and surfaces in R3. But now suppose we're back in R2, but we have no idea what this set looks like. Before we had a very nice set. We had very nice sets, and I told you what they look like, but we didn't have a parameterization. So now in general, so let's call this set A. In general, define, so you know it has to be something official when it has a nice little, nice script H. So again we'll do the exact same thing. So we're going to take the sum, we're going to take covers of our set A. A is a subset of the union of BIs, and we're going to add up. So this S is kind of how we're going to think about our dimension, right? So if I take a ball that's in my highest dimension and I intersect it with a set that I think is going to be S-dimensional, then I'll get an S-dimensional ball, right? And so we're going to approximate that by the diameter of BI all over 2. So again, this is just my radius. I'm going to take it to the S powered, right? And then I'm just going to approximate it by the area of an S ball, right? And so I'm going to throw in this silly factor there, which we don't care about too much. It's just a factor. It's just a constant that depends on S that makes it so our balls will have correct volume that we already know. Correct, whatever that means. So so again, I think I have. So I'll just close my brace there. Just close my brace. So
Well, that's the delta definition.
That's the delta definition. Very. Oh yes, very good. Oh, thank you, Michael. Thank you. I knew I was forgetting something. So the diameter, very good, of BIs are less than delta. Right. So we want to make sure that it adheres to it pretty closely. Then we want to keep track of that. And so then again, exactly. Oh, and then I'm always forgetting things. And so then we're going to take the infimum. We want to take the infimum over all these covers, right? So you take a cover. You cover your set by BIs. Take the cover of your set of BIs. Take any cover of BIs. B1, B2, B3, B4. So that A is contained in all these guys. You sum up the radii to the S power, multiplied by a funny constant, and then you take all these covers that satisfy the diameter condition, and you take the infimum over all those covers, and that's what we define as so it's H delta S of A.
So in R3, that blob would have 0 volume in it. So it depends on what you choose for S.
Very good, yeah. So that's the whole, yes, exactly. So S is an unknown parameter at this point. So S we're thinking about, so we've done the example, S is 1 for the length, right? So if this was, if S was 1, and this is just diameter of BI divided by 2, so you can guess what alpha of 1 is. It's 2, hopefully. So exactly. And so S is like a varying thing, right? So notice, so what are the two things I want to note here? So, so notice, oh yeah, so let's finish this. So then finally let, so then HS of A equal to the limit as delta goes to 0 of HS delta of A. So again, just for the exact same reason, this quantity is increasing as delta goes to 0, so we know we have that limit. It might be infinity. It might be infinity. So, okay. Very good. Very good. So exactly, so note S does not, in this definition, S does not have to be an integer. But it does, we do want it to be bigger than or equal to 0. We want it to be non-negative, but it does not have to be an integer. Or S bigger than or equal to 0. So students always hate it when you go back and add stuff. They sigh very loudly to let me know that I appreciate that. So very good. So this is I guess let's call this. This is HS is called S-dimensional Hausdorff measure. So I guess maybe I'll say, so alpha of S is merely a constant, so that when S is an integer, a positive integer, then alpha of n times r to the n is the volume of an n-dimensional ball. An n-dimensional ball of radius r.
So what does it mean to be in a non-integer dimension then? And then how can we use balls if we, because we use balls like if we like 3-dimension, like spheres. So how would that carry out if you're in like a non-integer dimension?
So we're always in an integer dimension. Like all our sets exist in an integer dimension, but we're saying that whatever. Okay, so I guess so it's not quite clear yet.
But you're measuring them S-dimensionally.
Yeah.
N's an
So
integer,
exactly.
S-infinity.
So you're thinking about how these balls intersected your set as being S-dimensional. That's how we came up with this, right? So that's why we're saying this is an S-dimensional measure.
So
yeah.
So could you make different choices for what alpha is for non-integers? Like, because you've got a bunch of points that you can just write.
Very good, very good. So yeah, you can do that, yes. But what's the point? I guess you want it to be, so you want it to be, so that's a really good question. So basically you're extending, you figure out what the function is. So this involves like some sort of factorial, right?
Right.
And so
oh, and then you extend to the
you extend analytically to the plane, which involves a gamma function. So I'm about to write that up. So alpha of n so if this is the dimension of the if this is the volume of the r-dimensional ball, alpha of n, you'll see this all the time. Alpha of n is the volume of just a ball of radius 1, of an n ball of radius 1. Right, so we want to extend analytically to the rest of the real numbers. So obviously I have to look this up. I don't want to tell you any lies. So alpha of s is equal to pi to the s over 2 all over gamma of s over 2 plus 1. Right? And so again, this is just, again, it's just to make the volume of the ball exactly like pi r squared, or 4/3 pi r cubed. So the question is, and that just comes from, where does that come from? That comes from knowing the area of rectangles, right, in geometry. And so the question is this isn't so great, it's nothing special. Why couldn't you just let the area of a ball be 1? Why can't you let the volume of a ball of radius 1 be 1? Right? It would throw away the area of a square off, but or a cube, but it doesn't matter. It's all convention, right? It's just off by a constant. So that's the reason I'm trying to emphasize it. That alpha of it makes it look so much scarier when you throw this alpha of s in there, but it's not so scary. So very good. So next thing to say, definitions. We call it HS the S dimensional measure. So note. Okay, so here's another note. And this is the reason I insisted on kept writing diameters. Our covers actually, and I actually left it out of the definition to begin with. Covers don't have to be balls. Don't have to be balls. It's a small, not quite trivial fact. They can be any sets, and if we know what's the diameter of any set,
We just did that.
Yeah, it's the supremum of the distance between any 2 points.
exactly right. The supremum between the distance of any 2 points is that the 2 points are my set. Right? So very good, very good. So you can actually cover. It makes it easier, and it'll lead to some very quick corollaries for some properties of the Hausdorff measure that we're going to use here in a little bit. So we can relax this condition that we just covered it with balls, but it's easier to see where this comes from if you cover it with balls straight away. Let's make sure I didn't leave anything out. Very good. Next, so here's another fact. So here's another fact. The graph of HS of A looks like. So now we want to ask ourselves, how does HS of A change as S changes? So hopefully you kind of got the idea that H2 should be something like area and H1 should be length. So here's my N, and here's what I'll call D. And always, and then if nobody complains, I'm going to put infinity on that number line. So always the graph of the Hausdorff measure of a set will look like this. For some D. For some D, 0 less than or equal to D, less than or equal to N. So it'll be infinity all the way up to a certain number, then it'll drop down to 0. But we don't know what HD of A could be anything.
Didn't you just say it was 0?
Those are open circles.
These are open circles, yeah.
Ah, okay.
So these are open circles, yeah. And so and I didn't want to put HD of A anywhere. So,
But is that point going to land on the dimension of the set?
I'm sorry?
Is that point going to land on the dimension of the set?
So it depends what you mean by land on, right, Eddie? So we don't have a dimension yet, right? So very good, Eddie, very good. So does not have to be an integer. Oh, that's the multiport. So HD of A can be anything. So 0 is less than equal to HD of A. Is less than equal to infinity. So it can be anything, but that doesn't matter. So exactly as Eddie said. So we can define. We call D the Hausdorff dimension. So that's the reason I asked Eddie. So does it land on the dimension? Well, we don't even know what the dimension is yet. So we call D the Hausdorff dimension.
And it could be infinite dimensional.
It could be. No, it can't be. It can't be infinite dimensional. Very good. So very good. So it can't be infinite dimensional because the set is
strictly lesser.
The set. So this is the measure. This is the measure of A. The d-dimensional measure of A.
Okay. Yeah.
That could be infinity.
Okay.
But D cannot be infinity.
Right.
Because it exists in Rn.
Right.
So something in Rn can't have more than n dimensions, right? In theory, right? And so, and not in theory, in fact. So, but I haven't even said what this is yet. So let's call it dimension Hausdorff of A. So we're just going to say, well, it's the infimum. So again, we have to define it mathematically. Overall S such that Hs of A equals 0. Right? So if you go up high enough, so notice you can, even if you're in Rn, you can still let S be bigger than N. Right? If S is bigger than N, then H and A is in Rn. A is a subset of Rn. Then obviously, like I just said, you can't have something of higher dimension in Rn. So Hs of A would be 0. So this makes sense. So there exists S's such that, but it can be n-dimensional. Surely you can have something n-dimensional in Rn, right? And so this is called the Hausdorff dimension. And so you just look at this graph, and sure enough, wherever this happens, that's your dimension, right? And it's the same thing as saying the super overall dimensions. I gotta be careful here. So yeah, exactly. So that's the reason you can't define it as the sup, because you don't know its infinity anywhere. You can have H0 dimensional finite. So we don't know what H0 is yet. I'll tell you what H0 is. Maybe I should make you figure it out. The what? I was wondering about that. I don't have there's no clock. It's what? 6:10. Oh no. I started at 5, right? Okay. Very good. Okay, so sorry about that. Okay, so very good. So I get the Hausdorff dimension and the Hausdorff measure. So okay, so sorry about that. So I'll finish here in 2 minutes. So luckily there's not as many people.
If people need to go, they can. And we can just
Yeah, if anybody, sorry about this.
You wouldn't be offended?
No. I'm lucky there's not more people in my class here because they'll let me know that my time management is not good. Because I always tell them that they should have showed up to let me know that my time management is not good.
We'll mark it on your evaluation.
Okay, yes. Exactly.
But yeah, anyone who needs to go, feel free.
Okay, yeah, no hard feelings. I have, yeah. So facts about Hausdorff measure. So here, let's have a few. So one in Rn. So notice, so in Rn, Hn is equal to Ln. So in Rn, we always have our Lebesgue n measure, right? And so in Rn, my top dimensional, this guy, measuring it. So this is basically saying that measuring it with cubes of highest dimension or measuring it with spheres of higher dimension, it's going to be the same. So that seems about right. Actually, we didn't even need to measure it with balls that I claimed there, but H0 is counting measure. So H0 will just tell you how many points are in a set. So this is a neat little exercise. You can do that. H0 of A equals a number of points in A. Right? Okay, and then 3. Lambda is bigger than 0. HS of lambda A. So you take a set and you blow it up by lambda, then you're going to affect its measure by lambda to the s. S of A.
So do you find the center? You find the center of the object, and then how do you blow up an object?
Oh, very good. Yeah. So suppose it's an Rn, right? And so lambda A is just equal to the set of all points lambda x, such that x is in A. Right. So everything's in Euclidean space, and even like a vector space are the reals, and so you can just multiply by a constant exactly. So yeah, exactly. So it just makes everything that much bigger. And this should be clear. It should be clear if something is integer dimensional, right? So this is regular from n-dimensional. If you make a cube twice as big, or if you make a square twice as big, then its area will be 4 times as much. So 4 HS is translation, and rotation is variant. So if you take a set and you move it, or you take a set and rotate it, it won't change the measure. Right? So HS of P plus A equals HS of A for P in Rn. And same thing with rotation. Right? And then 5. So then the final thing you should ask, and this is HN HS agrees. H2 agrees with surface area in R3, and H1 agrees with surface area of a differentiable surface and and H1 agrees with the length of a differentiable curve.
Do P and A have to be the same dimension?
Say that again?
Do P and A have to be the same dimension?
Yeah, it just means like.
Okay, that's. But then you don't know what A is, right?
No. You could translate the surface. So.
Like A consists of points in Rn, so you.
Yeah.
So you just translate all the points.
Okay.
So it's just saying that this set I have right here. Here's my A. If I move it by P, then the S dimension of this set will have the same S dimensional.
Okay, I was just under the assumption that we didn't know what dimension A was in.
We know it's in Rn. We just don't know its opposite.
So we know A exists in Rn,
Okay.
and from but we can find the dimension of A once we have this tool, once we have this new Hausdorff measure. Right?
Okay.
So once we have this new, so the point was, is like when I first had a general set in Rn, I had no idea what dimension was or how to even think about it, right? So now I can take any subset, I can find its Hausdorff dimension, and then that's all. Then that all works out.
So like outside of like intuitively working, if we wanted to show it was invariant, we would find the dimension of A first, then take something in that same thing, and like shift it or something.
No. So this is for you don't have to know what the dimension it is before you shift it.
Okay.
So it lives in Rn, so I can just whatever set it is, I just have to translate the set. Right? I don't have to know what dimension it is before. This will be true no matter what dimension. Like, so I mean, if it's infinite dimensional for this S, if I shift it, it'll still be infinite dimensional, even if it's not the dimension. So this is true for all S, not just the dimension of A. Maybe that's your question. So notice this. Yeah, I can apply HS to any set I want, not just if S is the dimension of the set. So yeah, so exactly. So what does this mean? So if S equals some phi of U, or phi, so S is the surface that's the image of a phi. So this is what you always see. So you saw this in so here's my phi U in R2. So this was in vector calculus. And here's my phi parameterizing my surface, right? Then magically H2 of S is equal to the integral over U, just phi U cross phi D magnitude du dt. So magically, this way we've defined this Hausdorff measure, it exactly agrees with our original idea for this differentiable sets. And this is hopefully, I mean, this is a very important fact, right? If it didn't, then we've done a lot of work that was not familiar to us. So sorry, yeah, sorry I didn't get to as much as I was hoping to, but hopefully you agree that Hausdorff measure is useful. I don't know. I think I better stop here. Questions?
What is the dimension of Cantor set cross Cantor set?
Very good. Okay. Oh, Eric, you just you didn't even know that. Anybody can leave if they want. I guarantee you I won't have any hard feelings, but I really, I'll tell you guys this. So I'll do this really quickly. So start out with E, right? So maybe you guys have all seen the Cantor set before. So start out with E and R2. This is just a rectangle, right? And then take out, and then now draw this set. So this is E1 actually. This is E2. So draw a tic-tac-toe and take out everything but the corners. And then erase these lines. So I'm taking out, so basically I'm taking out this cross piece from this guy. This is E2. E3. So then we do the exact same thing to each one of these guys. So and then this guy. That's E3. And then E4, E5, E5. And then so then you let E just be the intersections. These are all closed sets. They're all contained in each other. So I mean, they don't even contain each other, but we'll just let E be the intersection of all these closed sets that are successively containing each other. E is just the intersection over En. So this is exactly, so if you see the Cantor set, this is the Cantor set across itself, exactly as Eric said. And so now we want to know the dimension of this. So I claim it's very easy from the properties that I've written up here, technically the property that I just erased, Hs of lambda A is equal to lambda to S Hs of A. So I claim, so this is what's called a self-similar set. So I won't write it out definition for you, but it just means I can take a piece of it and blow it up, and it looks just like the original guy, right? And so And so let's take this piece right here. Technically, these guys shouldn't be here. Anyway, so this I've done this many times, and so now my E is all full of holes now, right? So here's my E. So he's all full of holes, and I don't know what he looks like. But let's call, so now I can say that, let's call this set x1, this set x2, this set x3, and this set x4, right? So we want to find the Hausdorff dimension, the dimensional Hausdorff of E, right? Right. So first thing we're going to assume, we're going to call this D, right? Assume HD of E is assume bigger than 0 and less than infinity. But this is a big assumption. This is a big assumption.
Wouldn't
So
you sort of think it was 0? I would sort
When
of
you think it's less
0.
than 2?
You would think it would be
I would
0.
think
You
it's
would think the area of it would be 0.
Yeah, that's
right?
what I was thinking.
Yeah, the area of it would be 0.
Okay.
But we're not sure. So the whole point of this dimension, the whole point of this Hausdorff measure is to pick the dimension that would give you a finite number, right? But that might not be finite. Well, what is E? Well, E is just if I took x1 and I blew it up by 3.
Well, but we know the Cantor set has a positive dimension.
Uh-huh.
And so we would expect this also to have a positive dimension.
Yeah, I mean, well, any set's dimensions are going to be positive. I mean, non-zero. Non-zero, yeah. Yeah, but we don't even know what the dimension of the Cantor set is. But you do this exact same thing for the Cantor set. You can do this, so exercises do this for the exact same thing for the Cantor set, because the Cantor set is. So you know, you can do this exact same thing. So you know HD of E is equal to HD of 3 times x1. Sure. Right? So, but at the same time, HD of E is also equal to, if I just took HD of each one of these pieces, right? These pieces are completely disjoint, so if I took the HD of each one of them and added them together, then it should be the same, right? So HD of x1 plus HD of x2 plus HD of x3 plus HD of x4. Right, so now we're going to use our 2 facts that I wrote up here. So the first thing we're going to notice is that if I pull this 3 out, what am I going to have to do to the 3 if I want to pull it out?
Raise it to the S, D.
To the D, right? Exactly, right? So yeah, exactly. This is D here. So I'll pull this 3 out, and so I'm gonna equate this to this guy. H3 HD of x1. But at the same time, it's also translation invariant. So all of these guys should be equal to HD of x1, right? So we have 4 of these guys sitting right here. So hopefully you know now why I had to assume it was non-zero and non-infinite. So since 0 is less than HD of x1 is less than infinity, we see that 3 to the D is equal to 4. Or D, or, so what do we do? That's my
1 base 3 of 4.
Yeah, so take log on both sides, right? Log. So log of, so we want to solve for D, we take the log of both sides is equal to log of 4. So we get that D is equal to log of 4 over the log of 3. Right? Exactly. So you do this exact same thing for the Cantor set. So C is the Cantor set. you'll get the dimension of Hausdorff dimension of the Cantor set. This is equal to the natural log of 2 over the natural log of 3. And that's do the exact same thing. So notice this thing, so notice this is between 1 and 2. This is between 0 and 1. Right? If I take a line and I start taking out pieces out of it, this will be between 0 and 1. If I take something that's two-dimensional and I start Swiss cheesing it, it should be between, well, it can go down further than 1, I guess, but this is between 1 and 2. So and also I know, I'm pretty sure h to the natural, so we have to do more work to find hd of a, but have to do more work. To find of e, to find h of the natural log of 4 over the natural log of 3 of a. But the nice thing is, for covers that decrease in diameter, you can actually use these ENs. And using these, I think you can actually show that it is 1. I know for a fact that the h to the natural log of 2 over natural log of 3 of the Cantor set is 1. And you show that using the covers, and you use as covers of shrinking diameter, you use as the original sets you used to construct it.
So well, when you find the Hausdorff measure of something using its own dimension, will you always get 1?
No.
So that's special.
Yes, yeah. It is definitely special, yeah. So, exactly. So remember I claimed at the very beginning that the Hausdorff dimension of a set could be anywhere between, could include 0 and go all the way up to infinity. Right? I think for self-similar sets, you might be able to say something more specific, but I'm not sure. So self-similar sets, you might be able to say, you'd have to maybe put a few more conditions on it. Very good. So you can use, so for exercise, you can do the Cantor set, and if you know another example is the Koch curve. So if you want to do the Koch curve, is just take an equilateral triangle. You can take an equilateral triangle, and then you take out the middle third, and you jump it up, and you repeat that over and over again on each side. And this is a little bit different because you start with a one-dimensional, and it starts getting longer and longer, and it ends up being higher than one-dimensional, as opposed to starting with something one-dimensional and gets smaller and smaller. You take away stuff or add stuff to it, so it's a little bit different. And finally, so yeah, again, I apologize for going so far over, so you guys can, but I want to recommend a NOVA that I saw many years ago. It came out in 2011. But it's called Hunting the Hidden Dimension. You seen it?
Yeah, it's on YouTube. Right?
Okay, it's on YouTube?
I think it's on YouTube.
Oh, I looked up on PBS's website the other day, and you can't watch it for free anymore. You have to pay like $2 to watch it.
Was this a BBC documentary?
No, it's just Nova.
Oh,
Nova, yeah. So that's that, and then so another thing is this originally you can also ask. It's also commonly called what is the dimension of a coastline. So you can think about coastlines and circulatory systems and forests and trees as self-similar sets, and so they talk about that in the video. And so Mandelbrot originally, okay. So I'll just say this. Sorry. So sorry about this. So finally the punchline is, I was about to say this. So the definition of, so the last thing we say is the definition of a fractal, right? So you all don't know. So I heard a couple of talks where the person says that there is no definition of a fractal, but technically the definition of a fractal is a set whose Hausdorff dimension is not the same as its topological dimension. So I won't know what the topological dimension is. But in particular, topological dimension has to be an integer. So anytime a set has a fractional Hausdorff dimension, you know it has to be a fractal. So Mandelbrot was the first one to sort of look at these, and he wrote the paper, How Long is the Coast of Britain? So he estimated the coastline of Britain to have a Hausdorff dimension about 1.25. So those are some things you can look at. Sorry.
All right.